special thanks to Dr. Desched and everybody in the machine shop for letting us use their equipment. My name is Calvin Metcalf. This is Otto Newman and Brian Bradley and Nico Jen, who's sitting right up there. Put your hand up, Newman. We did the zero gravity arm. So I'm going to give you a brief agenda. Just introduction, need and goal statement, a little bit of literature search. We're going to take you through our design, testing results of our design, and then we also have a cost allocation slide, which we feel will be very beneficial to campuses. Future recommendations, and then we'll end with any questions you might have. Very briefly for our need and goal statement. Our need statement is the client has very little movement and muscle strength in his or her arm, and is not satisfied with their ability to support the arm without the assistance of another person. The client is in a wheelchair and would like to be able to have their motion in their arms so they can extend, retract, move vertically and horizontally with assistance from a mechanism rather than another person. Which led us to our goal statement, which states we wanted to design a mechanism that supports an arm for a full range of motion in the X, Y, and Z directions that can assist in the everyday tasks that a person in a wheelchair with little muscle tone in their arms can't achieve without human assistance. So the first thing we did when we decided to do the zero gravity arm was to do a bit of research, obviously. We came across a company called Equipoise, and they currently manufacture the world's first exoskeletal arm support for manual tasks, and they called it the X-arm. The problem is with this design is that it's very costly, between $2,500 and $5,000. So what do? We contacted Equipoise, we sent them an email, and they redirected that email to Tony Sackstetter, who's the Vice President of Technologies for the company. And he was very interested in our project, very helpful, gave us good advice. There's a few things we took out of it that he said. He said, prototype early and often without fear of failure. You learn more from a failed prototype than a successful one. Know what questions you expect the prototype to answer. And plan the prototype accordingly. We felt this one was very important. The second one we took from it was how the machine contacts the body is critical, which you'll see later. And rigidity improves responsiveness, which you'll also see later in what we've designed for. We looked at some of their mechanisms. We came across this one, which is the Zero G. It's designed more for heavy-duty use, heavy drills, cameras. You find it in those aspects. And then we also went back to the basics. We looked at things such as lamps, things like that with zero gravity concept. These are our design objectives and constraints. Affordability, we wanted to keep the material cost under $250, and then the total cost per unit below $400, which we feel is significantly lower than the $2,500. Minimal force input was half a pound. With very little muscle tone in your arms, we felt half a pound was a good number to move your arm down, up, anywhere you wanted to move it. Horizontal motion, we said approximately 150 degrees from the right side of your body, and 0 to 70 degrees in vertical motion from the chair, the arms of the chair. We wanted to support varying arm dimensions. We initially had 10 pounds. A human arm on average weighs 10 pounds, but that's not connected to the body. When it's connected to the body, it's significantly less. Full range of motion, 2 to 3 degrees of freedom inside working envelope, which Ryan will explain to you later. Durability, for the mechanism itself, we felt 5 years was a good number, with adjustments here and there. And for the rubber bands, which we'll explain to you later as well, we said 1 year. Rubber bands over time might not keep their strength. Effortless movement, 5 inches of translational movement per second, which also takes us back to rigidity. And we wanted to keep it safe, no pinch points, sharp edges, or unsafe failures. So I'll leave it to Otto to explain our design concepts.
So for our concept phase, we went with a cascading design process. We, as Tony Sackstetter said, we wanted to prototype early and often, so we went with simple concepts that we could try out and experiment with. We initially went with trying to replicate the floating lamp. We also added another point at the end where the arm could extend further using the spring. Overall, we weren't happy with the freedom and movement this gave, so we went on to our second design concept. We tried moving the rotational joint from the base of the mechanism out to where the arm was, and maintaining the floating lamp kind of design with the spring there. Again, we didn't really feel we had the working envelope we wanted, and we had a lot of trouble with having a linear spring to support the 0G. So our final concept before we went on to the serious prototyping phase was when you see in concept 3. We were very unhappy with not being able to use a computer to do the 0G. Our original idea was like a steel manifold to press in the springs laterally and preserve 0G no matter where the arm was. We also added a rotational pin at the top to give an additional degree of freedom in the working envelope. And so finally, as Tony Saxter said, we started prototyping, and we came across our first design attempt. When we were adding the rotational arm to the top of our concept, we realized that we wouldn't keep the moment neutral about that top head. If the arm was out, extended all the way, 0G would begin to fail and fall. Conversely, if it was pulled in, 0G would be too strong and would pull the arm up. So what we decided to do was add a counterweight. But the weight always wants to go to the lowest point, and if the head was never level, it would force the arm forward or back, which is very undesirable. So what we did is we used Mach 325 closure equation to determine what geometry we would need to maintain that parallel over the widest range, and we generated a Java program to iterate through all the different possible geometries to optimize our design. Secondly, we were trying the lateral displacement of springs when we realized that they plastically deform if you leave them laterally displaced. This was very, very unacceptable, as we can't have our springs breaking all the time. So the solution was, for our third design attempt, to move the springs back and displace them linearly. The issue with this design was we had very little cam size. As you can see, where the cam was displaced in the second stage of the spring box there, is very small relative to the overall size of the spring box. And secondly, after playing with this mechanism, we realized that the cable required to hold the springs also was very abrasive with the aluminum. And after much playing with it, we began to realize that it was sawing our design apart. We decided springs wasn't what we were going to go with, and so for our final design, we modified things a bit, and I'll hand you off to Ryan